All right, let's go ahead and get going. Let me see. All right, so we are going to continue our discussion of sort of the basic structure of classical field theory and its applications to different soft matter systems. Um, and last time we basically got through the whole particle to field transformation, right? We went through the math for one of the ways of going from a partition function that might take the form integral dr to the n e to the minus beta eu, the sort of standard classical form. And we showed that we can, at least formally exactly, transform this into something with a slightly different prefactor, and then with an effective Hamiltonian. This guy should still have 1 over n factorial, and probably also the Vn needs to stay explicit there. And the Hamiltonian we saw had this kind of general form. Right, we had introduced a field, and this is the case for a single component system. We had one field u of r, the functional inverse of our parapotential, and then the field at a different location. And then we had minus n log q of iw. Right, and so some of the key things that we saw last time were that, first of all, we have this imaginary unit floating around, so that kind of complicates things, complicates sampling this thing. And the general structure that we have is that we have these this Gaussian form in the potential fields w of r, and these things are coupled at 2 different locations through this inverse of the parapotential. And so that was a really nice interpretation of this that I believe it was Carol that mentioned last time. And today the whole goal is basically going to be to go through this particle to field transformation in a bunch of example systems. And once we've gone through the particle to field transformation, we'll also see what we can say using mean field approximations and things like that. But today is going to be mostly applying what we've come up with to a couple of example systems. And so the first one that I want to start with is going to be just a 2-component system where we just have a mixture of two simple fluids. We're just going to call them A and B. Okay, so we'll start with our 2-component system. And what we're going to get out of this is basically the regular solution theory at the end. So we're going to say that we have a total number of molecules in T. That's going to be the number of A plus the number of B that we have. And we'll define our average density as just NT over V. And we'll also have volume fractions. VA is going to be NA over V, and VB is going to be NB over V. And really, this should be NA times the partial molar volume of A divided by the total volume, but I'm just going to ignore the partial molar volumes, and we're going to assume that they're actually equal. All right, and so last time we started by defining the microscopic density operator, this rho hat, and now because we have 2 components, we're going to have 2 of those operators. So we will have a rho hat A of R, and so this will just be sum over all of the A particles, R minus Rj. Similarly, we'll have a rho hat B of R. And I'm also going to go ahead and define one of the other microscopic density operators that we're going to need is this rho plus, which is just the sum of the 2, right? So it tells you about the spatially varying total density. A of R plus rho hat B of R. All right, and we're gonna define our parapotential to be just something that's about the simplest thing that we could possibly imagine. We just want there to be some sort of energetic penalty for A and B to be next to each other. And so we're going to say that our parapotential, this U of Rij, is going to be Kt times chi, which is, again, it's sort of an energy of putting I and J next to each other. Ri minus delta of Rj. And so it's purely local because we have this delta function interaction, right? So our particle I and particle J only feel each other if they are like mathematically exactly on top of each other. And otherwise they don't interact with each other at all. Um, and and the strength of that interaction is modulated by this parameter chi. And so we're just going to call this the chi parameter. And we're going to assume that chi is a positive number in this case. And the other assumption that we're going to make is that we have an incompressible system. And we'll see how we enforce that in a field theory. All right, so with this definition, our total potential energy is going to be beta u will just simply be chi integral dr integral dr prime rho a hat of r u of r and rho hat b of r prime. And we can write down our partition function. So we write down the particle version of our partition function where we still have some prefactor that generally has like the de Broglie wavelengths, stuff like that in it. We have an a factorial and an b factorial. E to the minus beta u. Actually, let me put this, I'm just going to go ahead and write this out in integral form. So we have minus chi delta of r minus r prime and rho hat b of r prime. And then the other thing that we need to insert in here, so I'm going to use a brace to make sure that it's clear, is that this is going to be multiplied by a delta functional that's going to enforce the density to everywhere be equal to rho naught. And so this is going to be the thing that enforces our incompressibility constraint. All right, so it's going to be rho hat plus minus rho naught. Okay, so the first thing that we notice here, though, is that the approach that we've been taking in deriving the field theories has been to use the Hubbard-Stratanovich transformation, which requires us to have Gaussian integrals. And so the first problem that we might notice is that we don't actually have a Gaussian form, right? We have rho A times rho B, and we need this to be something like, some f of r times with the function with the interaction potential in between f and multiplied by some f of r prime. And so we have to manipulate and play around with this thing a bit to get it into a form that we can work with. And so the way that we're going to do that is to introduce another microscopic density thing that gives us the difference in the densities between species A and B as a function of position in space. All right, so we'll introduce this rho hat minus of r. And make sure I get my signs right. So it's going to be rho A of r minus rho B hat of r. Right, and so this tells us about the local composition variance. And with the definition of rho plus above and this definition of rho minus, we can rewrite rho A hat of r. Right, so rho A is just going to be 1/2 the sum of the two plus rho hat minus of r. Right, because if you remember, rho hat plus was A plus B. So if we just add the two together, the B's cancel out and we get 2 factors of A. And so we have to divide by 2 to kill off that second factor. Then rho hat B of r is just going to be of course, the difference. So it's going to be 1/2 rho hat plus of r minus rho hat minus of r. And so if we plug this into the double integral that we had above, right? So we plug into beta u. And I'm just going to focus on the product of the rho hat A times the rho hat of B prime. And what we get is that we'll have rho hat r for A times rho hat B of r prime. And so then this is going to be, let me make sure I don't mess this up. So we'll have rho hat plus of r plus rho hat minus of r, and then times another 1/2 rho hat plus minus rho hat minus of r. And then when we multiply everything out, the of course, it's straightforward multiplication. Everything is the middle terms are going to cancel because we'll have a plus rho minus times rho plus, and then a minus rho minus times rho plus. And so it's only the quadratic terms that survive. And so we have 1/4 rho hat plus of r squared. Sorry, in this second term, I need to be clear that this second term should be at prime. So let me r rho hat plus of r prime. And then we'll have minus the rho hat minus squared. Well, rho hat minus of r times rho hat minus of r prime. Okay. And then, so now we can actually plug this into beta u, or into the pair potential. So now we have chi integral dr prime. And I'm going to bring the 1/4 out into the prefactor. And so then we will have, let me see. So I want to make sure I get this clear. So rho of r, delta of r minus r prime, rho hat plus of r prime, and then minus rho hat minus of r, delta r minus r prime, rho hat minus of r prime. All right, and all of this is still under the integral sign, so make sure that that's clear. So the first term, rho hat plus, we're enforcing the incompressibility constraint. So this is everywhere just going to be equal to rho naught, right? So we can just simply say that this is rho naught because of incompressibility, right? And so then in that case, we can just analytically evaluate that first term, and it's just going to give us some constants that we can lump into the prefactor of our partition function. And the only one that's really going to survive is going to be this second term that's going to be like negative quadratic in rho hat minus. Right, so those will be the only terms that stick around with us. And so in the end, what we're going to get is something where, right, our exponential of minus beta u, this term is going to become, so we'll have an exponential, and I'm going to separate out the term involving rho hat plus from the terms involving rho hat minus. So we'll have chi over 4. So we have two factors of rho, so we're going to have rho naught squared. One of the integrals is going to just give us the delta, is just going to kill off the delta function, so that won't do anything. And then the other one is going to give us a factor of volume, but it's also just a bunch of constants, right? So it's not really giving us anything that we need to be overly concerned about. And then the second term is just going to give us, let me see, just simply exponential. Now, because we have this minus sign in here, it's going to be plus chi over 4 integral dr prime rho minus hat of r delta function rho hat minus r prime. Right. And now this is a thing that's in Gaussian form, right? So we can use the second Gaussian integral that we introduced in the first lecture, and we can write this whole guy in terms of the of an integral over the fields. And so what we're going to do is use, so let's see, I'm going to take, so the second exponential, right, this is going to let us introduce a field that's going to be conjugate to this rho hat minus. Right. Right, so we'll have this exponential chi by 4 integral dr prime rho hat minus r delta function, r minus r prime, minus r prime. This will be equal to, so the field I'm going to label with a subscript minus to indicate that it's conjugate to rho hat minus, and just using the usual Gaussian form that we have, it'll be exponential of, now we have this prefactor in here, and so when we invert that using the Gaussian functional integral, that actually ends up killing off the factor of a half, and so it's just -1 over chi is the prefactor here. The other important point is that the functional inverse of a delta function is another delta function, so we can exploit that and go ahead and take one of the integrals over the delta function, and we just end up with integral dr w minus of r, and then this whole thing squared. And then we have the term that still couples the microscopic densities or the particle positions to the field W minus. Right, so now we still have this plus integral dr W minus of r rho hat minus of r. All right, but we've gotten rid of the interactions between the microscopic particle positions, and now the thing that we have to worry about is this are the interactions of the particles with the field. All right, so that takes care of the potential involving chi. The incompressibility thing, we wrote down also that we can write a delta functional in a field theoretic representation, and so we can write this guy as integral dw plus e to the I integral dr. This is w plus of r, and then this is multiplied by rho hat plus minus, minus the constant rho naught, right? Because it's going to be the field that we introduce is conjugate to the argument of the delta function. But again, the thing that comes out of this is that we just have this rho hat plus that's going to, where we have particle coordinates that will interact with the field W plus. All right, so we take all of this hot mess. Oh, and I forgot something. There should be a prefactor in here of 1 over the normalization constant. I forgot to include that. I like to keep track of these things. Yeah, that it is important to make sure that that's there. All right, and so the way that this works is now we plug everything back into the partition function, and I'm going to skip some of the algebra so we can. So we will have z equals, and a lot of the prefactors I'm just going to kind of absorb because I don't want to keep writing out these horrifically messy prefactors. So we'll have constants that show up from, we have a new family of constants from this term. We have our NA factorial and B factorial. The omega 0, the prefactor of the Gaussian, or the normalization constant of the Gaussian, that's also getting buried in Z1. And then what we have that's going to survive is I'm going to rewrite. So we have an integral over W plus, W minus, and then I want to collect all the terms that only involve the fields. And so we'll have an exponential of -1 over chi integral dr W minus square root of r, right? So that comes from the Gaussian integral that's at the top of the screen. The other place where we have a term that only involves fields is this I W plus minus rho naught, right? That doesn't involve any microscopic density, so we don't have to concern ourselves with that. So I'm just going to tack that guy on. So we have minus I rho naught integral dr W plus of r. All right, so that kills off that takes care of the terms that only involve the fields. And then, the particle positions that we are integrating in over in our partition function, we can separate those out into the two groups, those that belong to particle A and those that belong to particle B. And the other thing that we can do is write rho hat plus and rho hat minus in terms of the densities A and B. Right? So if you remember, rho hat minus was A minus B, and rho hat plus was A plus B. And so this also gives us a collection of terms where we can just basically collect all of the terms that only involve the coordinates of the A species and the terms that only involve the coordinates of the B species. Right, so we'll have a dr to the NA exponential of, make sure I get this correct, minus integral dr rho hat A of R. Right, so we have rho hat A multiplying IW plus here. So we'll have an IW plus of R. And then we will also have plus W minus of R. Right, and that's everything that depends on rho hat A. And again, the plus W minus comes about because of rho A multiplying the W minus here. And then this is also still going to be multiplied by dNB exponential minus dr rho B hat of R IW plus of R, right? So W plus shows up in the same way. And the only thing that's different is that the sign on W minus flips. And all of this is still inside this horrific integral. But now this still, if you remember from last time, if we just look at one of these terms, right, if we just focus on like the rho A terms, this looks just like what we had for the simple fluid field theory when we converted this term into the molecular partition function. Right, we have a microscopic density multiplied by a field. In this case, the thing we're multiplying by is a sum of two fields. But if we were to make the substitution, like we just called everything in here equal to some, say, mu A of R, and everything in here equal to some mu B of R, then it's just a density times a field, right? And so we can make that kind of a change if we want. For this case, I'm just gonna leave it the way that it is. But regardless, we can now write this, use the substitutions that we introduced last time to write this whole middle line and the whole bottom line as an n log q type of contribution to the effective Hamiltonian. And I once again have a sign error that's goofed up somewhere. Let me see if I can find it real quick. If I can't, we'll just let it go. This looks right. Oh well, we'll just let it go. Maybe the error is in my notes. So let's see. Okay, so now we replace these terms with n log q. And our partition function, again, still no approximately equals. It's all still quite exact. We have our z1. When we introduce the n log q terms, that's when we pick up the v prefactors. And now we'll have dw minus integral dw plus exponential minus h of w minus w plus. And so now we have everything governed by our effective Hamiltonian. Our h of w minus w plus is then has the total form of integral dr 1 over chi w minus squared of r minus I rho naught w plus of r. Then we have minus na log qa. And instead of just having a simple IW argument, it's going to be I w plus, and then it's basically going to be what we were calling mu A, or what I called mu A above, but I'm just going to write it out. So it's going to depend on the sum, and NB is going to depend on the other one. Right, and then, of course, we have Right, so our QA is going to be 1 over V integral dr exponential minus IW plus W minus. That should be parenthetic. And QB is 1 over V integral dr e to the minus IW plus minus W minus. Okay, and so this is for this relatively simple system with simple interactions, we can sort of understand this. We can assign a physical interpretation to a lot of this pretty easily. So the W plus field shows up in both molecular partition functions in the same way, right? It's e to the minus IW plus. And that makes sense because the incompressibility, the W plus field came from the incompressibility constraint. So that's one of the types of interactions in our system. And it acts the same on both species, right? There is no distinction between A and B. It only cares about the total density. And so this thing is just going to serve as something that's going to force the system to have a constant density everywhere. The W minus field, on the other hand, is something that's, if you remember, it was conjugate to it came about from the chi interaction, and it's conjugate to the density difference between the two species. And so the way that this works is that it's going to drive concentration differences between component A and component B. And you can see that if W minus is locally a positive number, that's going to be something that's going to, I guess, energetically disfavor A, because it's going to make the argument of this exponential, a larger positive number. And so the e to the negative of that's going to be smaller. And in that same location where W minus is a positive number, it'll make it sort of locally favor B. And so that's how it can sort of drive local phase separation in the system. Okay, so that's how we work with a two-component system and get the exact field theory. And now we can start dealing with some of the approximations that we can make to simplify things. And so this is where we can start to make some connections to some of the more common ways that people implement and think about field theories. And so the first thing that we will start with is the mean field approximation. And the whole idea here is that we're going to start by, we again have our partition function, b to the n total, and a and b, and then integral dw plus, dw minus, e to the minus h. And of course, we remember that this partition function is always going to be related to the exponential of the Helmholtz potential, right, in the canonical ensemble, but it's going to be related to a free energy. And what we're going to assume is that these path integrals over the different field configurations are just going to be dominated by the one field configuration that minimizes the free energy of the system. Right? So we use our first approximately equals. And we're going to say that this is just e to the minus h of w plus star, w minus star. And the star is being used to indicate that these are the field configurations that minimize the free energy. Right? So w plus star, w minus star. And again, these are still generally going to be, spatially varying objects. And because of this relationship that we have between h and f, they're both e to the minus h and e to the minus beta f, and through the partition function, we can just as easily find the place where the functional derivative of h is 0 with respect to the fields, and that will also minimize the free energy of the system. So that's going to be our whole game for coming up with the mean field configurations. So So the way that we do this is we want to calculate W plus of R equals 0, and we want to calculate W minus of R equals 0. And generally speaking, if we were to take the the functional derivative of our Hamiltonian, we're going to get something with spatially varying quantities coming out of it. We'll work through the analysis of that momentarily. And generally speaking, the solution can have some sort of spatial variation to it. For this simple fluid example, it's the thing that we don't really care about the spatial variations, and so we're going to, for the moment, invoke yet another approximation where we assume that everything is homogeneous, right? So if we take the homogeneous mean field approximation, that means that W plus of R is going to be equal to just some constant, right? And it's our job to figure out what that constant is. Okay, so if we go back all the way up to our partition function, so up here what we have, we can start plugging in some of these things, and what we're going to have, actually let's just go ahead and start writing this out as a free energy. So I'm going to play a couple of tricks where I'm going to go ahead and solve this for the free energy. You can see that it's going to be exponentially related to the Helmholtz potential, and I'm going to leave this, let me just talk through it as I write it down. So we'll have beta f, it's going to be h, and then from the n factorial and the log of v terms, we're going to have minus na log of the volume minus nb log of the volume. Then from the na factorial and the nb factorial, we can throw Stirling approximation at that. So we'll have na log na plus nb log nb, right? So those prefactors give us our entropy of mixing. Oh, I forgot half of Stirling's approximation. That. And then we have plus F0, which is just going to be the log of that thing that I've been collecting and calling Z1, which is just a bunch of constants that we don't care about. And our H under this homogeneous mean field approximation. So if we're saying that W minus doesn't depend on position, we'll have 1 over chi W minus integral dr of just nothing, right? So there's just nothing there. So that'll give us a factor of volume, minus I rho naught W plus, again, integral of nothing because W plus comes through, then minus NA log Q A minus NB log Q B. All right, and yeah, all this simplifies pretty nicely. So now our QA, right, so QA just becomes 1 over V times the exponential of e to the minus IW plus W minus times, again, an integral of nothing, which is going to give us a volume and just cancel out that volume. And so this is going to give us just e to the minus IW plus minus W minus. Right. All right, and similarly for QB. And so since this shows up in the Hamiltonian as a natural log, we're just going to have NA times the field that species A experiences. And similarly for NB. And so for QB, we will have e to the minus I W plus and minus W minus. And so plug in the H. And what we find is that, so we'll have V over chi W minus squared minus I NA plus NB over V times W plus, right? And this NA plus NB over V is the rho naught. So I'm just writing that out in terms of the total number of species times V. So the volumes will cancel out. Then we'll have minus NA minus IW plus W minus NB IW plus minus W minus. And what we should hopefully see, if I've gotten my signs right, is that from the partition functions, the W plus is just going to drop out of the equation. And again, this sort of makes sense that W plus is going to end up being irrelevant because all it's doing is enforcing that the density is constant everywhere. And since we've invoked this homogeneous mean field approximation, the density can't be anything other than rho naught everywhere. And so we can just kind of take that as a given, and W plus really isn't going to play any role in the thermodynamics of the system. And so, right, so W plus drops out. And so that thing's gone. And now we can write down, so we plug in F V over KT. There's a bunch of, algebra, of course, that gets us here to this final step. So we'll have 1 over chi W minus squared minus VA W minus. So I've divided through by V so we can get everything in terms of volume fraction. W minus, and then plus the entropy of mixing terms. And of course, VB is 1 minus VA. There's a -1 and a minus F naught. And again, the constants I don't really care about, so I'm just going to call it minus little f0. All right. And finally, we can take the derivative of this thing with respect to W minus and solve for W minus at the minimum. Right? So take dF over V by dW minus equals 0 to figure out what W minus star is. So the derivative is, of course, trivial. We'll just have 2W minus over chi minus VA plus VB. And now we're evaluating this at the minimum, so we pick up a star on our W minus, because that's the one that minimizes our free energy, and we get chi by 2 VA minus VB. All right, and so then you plug back in. Again, there's some algebra involved that I'm just going to gloss over, and what you end up with. All right, so you plug in and simplify, and we'll get the regular solution theory as our result. All right, so F over V KT. This comes out to be chi. Well, it's something close to regular solution theory. VB 1 minus VB. And then we also have our entropy mixing terms. Actually, I'm just going to leave this as VA. See any reason to not do that? Plus VA log VA plus VE log VB. And then minus some constant, which is all the stuff that's kind of thermodynamically irrelevant. And so hopefully this looks like, if you have a chemical engineering background, you might know this is the one parameter Margulies equation. I usually teach this as regular solution theory derived from a lattice model. Or if you've seen the Flory-Huggins polymer solution theory, this looks like that model, except with one of the chain links set to unity. But it falls very naturally out of this the mean field approximation of this field theory. And so it's a really just kind of natural result that comes out of this. And of course, one of the things that we'll go over, I guess, starting next week is, different ways that we can kind of extend the theory to maybe incorporate fluctuations or to make more sophisticated approximations to the theory for maybe more interesting systems. All right, so that's basically what I wanted to say about the first example. The next two, I will probably skip a bit more of the algebra in the intermediate steps, but I'll try to be careful about defining the systems. Of course, all are welcome to ask questions if I do something that's not clear. So the next one is going to be just a simple system where we have a collection of charges, just a collection of point charges, but in an overall electroneutral system. And what we'll see is that the mean field approximation here gives us a really natural way of deriving the Poisson-Boltzmann equation. Right, so we can use field theory to derive Poisson-Boltzmann. All right, so we are going to, let me first write down our charge density. So we're going to assume that we have some microscopic charge density, rho hat C, and we're going to have a family of cations and anions. So all of the cations will carry a charge with valency Z plus. We'll have sum of J equals 1 to NC for cation. Rho hat. So my notes are written, defining this thing as rho hat plus, but this is, I want to emphasize that this is something different from the rho hat plus above. This is not the total density of anything. This is now the density of the cations. So make sure that that is clear to you, that this is cation density. And actually, wait. Sorry, this shouldn't be written that way. My notes are actually wrong. This should just be delta R minus RJ. Apologies. Then minus, right? So Z minus is going to be the valency of the anions, sum from J equals 1 to N. Where am I? Damn it. Delta R minus RJ. Okay, sorry, I kept looking at the wrong spot in my notes a couple of times. So make sure that the notation here is clear. So we're going from J equals 1 to N plus, and so that's the number of cations. Z plus and Z minus is the magnitude of the valency of the two different species. So we have both plus ions and minus ions floating around, and we have N minus of the total anions. And we're going to assume electroneutrality. So we have N equals N plus plus N minus total particles. And electroneutrality is going to require that N plus times Z plus, and then minus N minus times Z minus equals 0. And again, remember that Z plus and Z minus are the magnitudes of the charges, and so they are unsigned numbers. All right, and we're going to take all the interactions using, the full-blown Coulomb's law. All right, so our interactions are going to be through Coulomb's law. All right, so our U of R and R prime is going to be KT, times a Barham length over the magnitude of R minus R prime. And LB is the Barham length. So this is BJERRUM, so the Barham length. And this is going to be equal to the magnet, or the elementary charge value squared. Then we'll have KT permittivity of vacuum, and then there's some sort of relative dielectric. But we're just going to lump everything into the Barham length. And the Barham length, physically, it just tells you how far do you have to separate two charges before the interaction between them has the energy of KT. And we had written down the Coulomb's law earlier when we first introduced the particle to field transformation. And we had also written down the functional inverse of this thing. So we can just straightforwardly blow through the particle to field transformation. So we have U minus 1 of R and R prime. It has kind of this horrific looking form. So it's minus 1 over 4 pi LB grad squared of a delta of R minus R prime. So it looks kind of heinous because it has these weird operators just sort of floating around. But we will sort that out after we go through the Hubbard-Stratanovich transformation. And this thing in Fourier space, it's also a useful thing to have. So it's 2 pi cubed over LB, then k squared. All right, so our total energy, right? So our beta U is going to be 1/2 integral dr prime rho hat c, right? So the total charge density LB r minus r prime rho hat c at r prime, right? So all the charges at r interact with all the charges at r prime through Coulomb's law. Easy enough. And so this whole thing is already in Gaussian form, so it's going to be really easy for us to kind of blow through the particle to field transformation. So what we have is, for our partition function, we'll have z0 prime in plus factorial and minus factorial. And for this field, so when we do the Gaussian integral, I've always been using W as the field, and just to kind of make something that's a little bit more familiar with electrostatics, I'm going to use the Greek letter psi for this chemical potential field. Then we have integral dr to the n total, because we haven't gotten rid of our particle coordinates yet. Actually, I didn't even write down the particle version. Let me start by writing down the particle version just to make sure that this is all clear. Right, so we'll have exponential minus beta u. And since we're only considering, simple fluids, there's not really anything else. A simple fluid of charges, there's not really anything else to consider here. So since this is already in Gaussian form, we can go ahead and throw Hubbard-Stratanovich at it. So we'll have Z0 now we pick up our d psi dr to the n. Right, and so now the thing that we're going to have, the first term that we have to be a little bit careful about is the one where we introduce this functional inverse. And remember, it's going to be an exponential of whatever our field is. So this is going to be, make sure I get my prefactors right, hopefully. Well, so it's going to be minus 1/2 integral dr prime. We have our field at r, and then this is multiplied by the functional inverse of our potential. So minus 1/4 pi Ferrum length grad squared delta of r minus r prime. And then this is then multiplied by psi of r prime. Right, so all we did is plug in where we normally had our u to the -1. We just simply plugged in the functional inverse. And we'll talk through evaluating that thing momentarily. And then this is also multiplied by, so then inside this exponential, we also still have minus I integral dr psi of r rho hat c of r. Right, so that all goes back to this. Let me make that bracket a little bit bigger. So that's all inside that one exponential. Okay, so first let's focus on this term, right? The one that has the particle coordinates in it. We can go ahead and get that in terms of the monomer partition function, because that's a pretty easy thing for us to do. So it's an exponential with a difference in it, so we can make it the product of two exponentials, and all of the particle coordinates are not in the first one, so we can just isolate the term that has the particle coordinates in it. So we have integral dr to the n, then just simply e to the minus I integral dr psi of r rho hat c of r. And now we can plug in for rho hat c so that we can write it in terms of the positive and the negative ions. Right, so we can make this now integral dr n plus e to the minus I dr psi of r, and then we have the 1 to n plus delta of r minus, oh, make this a j, and then times z plus, and then all of that multiplied by dr to the n minus e to the minus I sum over j to the n minus r minus rj times z plus. And because I'm sorry, that should be a minus, obviously. And because we had the minus sign in the row hat C on the negative ion terms, this prefactor becomes a plus. All right, so we end up with just an overall prefactor. And now, again, this is in the form of sort of the standard molecular partition function form. And so we have an exponential with n plus independent terms. So we make that into a product of different exponentials. And then we end up with everything just kind of multiplying together. And so we end up with the first term becoming a VQ. We have a molecular partition function where the potential is just Z plus times psi, and all of this raised to the n plus. And then this is multiplied by VQ. And here we have minus IZ minus of psi, all raised to the n minus. All right, so that kills off the particle coordinate term. The other term that we have to worry about is this monstrosity. And the way that we clean this up is to just simply take the integral over dr prime, and that's just going to kill off our delta function and return the value of this other field only when r is equal to r prime, right? And so this is going to turn the whole term into psi minus 1 over 4 pi Barum length grad squared psi at r, right? And so it becomes a relatively simple term. And so what we end up with in the end is, so we have our new prefactor. We're going to have v to the n total, n plus minus factorial. Is that everything? I think I want to give a different index to this guy because it should have a normalization constant in it. So we'll just call it Z1 just to indicate that it's a little different than minus new effective Hamiltonian, and our H of effective Hamiltonian is going to be minus 1/2. So there's a lot of minus signs getting kicked around here. So in the original exponential, we have e to the minus, whole bunch of stuff, and then a minus sign in the potential. So that makes the exponential a net positive. But then the way that we define our effective Hamiltonian, we have a minus sign that we keep out front. And so again, we still need the explicit minus sign in the effective Hamiltonian. We perform the integral over r prime, so that term is gone, and we just have psi of r grad squared. Oh, sorry, forgot my constants. Psi of r, then minus n plus log q I z plus psi minus n minus log q minus iz minus psi. All right, we have our statistical field theory. I guess one side note that I have in here that I can talk us through is that this term, this first term, is often rewritten in another form using an integration by parts. And so we can talk through that real quick. So this first term is often rewritten so if we do an integration by parts, we have psi of r grad squared psi of r, and we start off by writing this as psi of r divergence of the gradient of psi. And then we do an integration by parts on this thing. And so this is going to be equal to, so now we're coming down using integration by parts. And so there's going to be some kind of surface integral. And because we're generally going to be interested in systems that have periodic boundaries, this surface term is always going to be 0, because on one side of the box we'll be integrating in the plus direction of a value. On the other side of the box we'll be integrating in the minus direction of the same value because it's periodic. And so that whole integral is always going to be 0. And then one of the gradient operators gets moved over to the other field. And so this just becomes minus dr grad psi dot grad psi. Or the way that this is typically written, this term is just going to be 0. And this just becomes minus integral dr grad psi squared. All right, so that gives us the final version of the Hamiltonian that we'll work with. So we have h of psi, and it kills off that minus sign in the front. The 1/2 combines with the 1 over 4 pi Barham length, integral dr grad psi squared, then minus n plus log q plus, minus n minus log q minus. And they still have the same functional dependence on the fields. All right, so again, we've gone through the particle to field transformation. We have our formally exact partition function with all of its glorious prefactors and everything. And the only thing that we'll do to sort of wrap up this this derivation is now we can invoke the mean field approximation. So we're going to say this guy, we have z1 v to the n minus factorial integral d psi e to the minus h. Again, we'll say that this is dominated by the mean field, and plus factorial minus factorial e to the minus h at psi star. And the thing that we want to find is the equation that results when we write d by d psi evaluated at psi star equals 0. Because that's going to be the thing that minimizes our free energy. And so if we let me see, where am I? So if we're take d by dh by d psi here, what we're going to get is, let me make sure, we have 1 over 8 pi Barham length, and then we have d by d psi of integral dr grad psi all squared. And this is one of the trickier functional derivative terms to work with, so we'll talk about that momentarily. And then we have two terms that are, d log q plus d psi and d log q minus d psi. And so those are, again, going to give us something like microscopic density operators for the cations and the anions. Right, so we'll have something that's plus I z plus rho hat of r, then minus I z minus microscopic density operator of r from the d log q terms. And then rho, this operator rho plus minus, is just going to be equal to 1 over v times q e to the, I guess, minus plus I z plus psi of r. Right, and that just comes from taking the functional derivative of that guy. And so when we take the derivative of this thing, I'm just going to write down the rule for it just because it's a known thing. It has kind of an unusual form, but what you get from this first term is that this functional derivative, this whole thing, is equal to minus, what is it, minus 2 grad squared psi of r. And so again, if you go through those expansions to derive the functional integrals that we did in the first lecture, you can prove this. There is some integration by parts and stuff to actually make it work as it should, but it is something that you can prove that this works out in this way. And so what we get in the end is, so the 2 is going to cancel out some of the part of the 8. So we end up with minus 1 over 4 pi Ferrum length grad squared psi of r from the first term, and then plus, so again, we have a density operator for the cations and the anions, and this just becomes plus I rho hat of the total microscopic density, of the total charge density of R, right, where we've defined this analogously to how we define the microscopic particle density. And this is, of course, all at mean field still, so that's now our mean field equation. And so if we rearrange this thing a little bit, what we find is that we get grad squared psi of R is equal to 4 pi Ferrum length I rho hat C of R. And hopefully this looks something very similar to Poisson's equation. And so if we kind of reinterpret this, if we sort of rearrange and collect and group an I with the field over here, we end up with grad squared. So if we multiply both sides by I, we'll have I psi of R. Then this will be minus 4 pi Boltzmann length charge density of R. And remember, this density operator already has the Boltzmann, it is already of this kind of Boltzmann factor form. So though the equation sort of naively looks like the full Poisson equation, you have to remember that because the form of the density operators, it has that Boltzmann distribution assumption that goes into the Poisson-Boltzmann equation built into it. But to me, this is a really nice and elegant way of deriving the Poisson-Boltzmann equation. And of course, you can go further from here and linearize it to get the even more simplified versions of this. All right, and this, if we just simply interpret this thing I times psi of R as the electrostatic potential, right, then this is all just entirely consistent with the Poisson-Boltzmann equation. Right? So you can see how that's you can see how that follows very nicely from this. Let me see what else. I think so. Going through these examples has taken a little longer than I thought. I had a third example set up, but I think I'm just going to skip that one so that we can move on to the polymers next time. I will copy and paste the part of my notes that works through the last example into this document before we post it on my group's website. So if anybody's interested in it, the notes will be there. So the other sort of interesting simple fluid that you can derive is a model for a thermotropic liquid crystal. So you can derive the Meyer-Soppe model for liquid crystals that will predict an isotropic to nematic transition. Again, using this very simple Hubbard-Stratanovich transformation approach. And of course, the nice thing about this is that none of these things are independent of each other, and they could all be combined with each other. Like you could very easily imagine making a system that has charges in it, but then also, there could be like an oil and a water phase that could potentially phase separate mixed in with that. And there's actually a lot of current interest in extending these field theories now to more sophisticated charge systems. One of the very nice things that's been going on in the Fredrickson group has been to introduce polarity into field theories so that you can have things like spatially varying polar and non-polar interactions, and that goes very well towards capturing things like ion solvation and stuff like that. So it's a really elegant way of extending the theory that we're starting to adopt a bit in my group as well. All right, but if there are no questions, then I'm going to go ahead and call it a day here, and we will pick up tomorrow, and we'll go through how we actually start integrating polymers into the field theory. And so that'll be kind of the next step that we hit. All right, have a good day, everyone.